Hey kids, welcome to section 5.3, inverse functions and relations. Today we're going to learn how to find the inverse of a function or relation, and then how to determine whether two functions are relations or inverses, or are functions or relations are inverses. So first let's talk about what an inverse function is. An inverse function is when you take one relation and you reverse the order pairs. So for instance, if you have a function that has 1, 5 as an order pair, the inverse will have 5, comma 1. If the function has 2, 6, the inverse has 6, 2. And if the function has 3, 7, the inverse has the order pair 7, 3. So inverse relations are when you take the order pairs and you swap the order. So for instance, if I want to find the inverse of this particular relation, all I have to do is reverse the order pairs. So -2, 9 becomes 9, -2. 4, -1 becomes -1, 4. -7, 9 becomes 9, -7. And 7, comma 0 becomes 0, comma 7. Make sure to put it in curly brackets because a relation is a set of ordered pairs. And if you don't have the curly brackets, you haven't written a set. All right, so example number 2, find an inverse relation. So we are going to, so the order pairs of the relation, are -8, -3, -8, -6, -3, -6. These are the coordinates of the vertices of a right triangle. Part A says to graph the relation. So -8, -3 is right here. -8, -6 is right here. Okay, and then we have the order pair -3, -6, so right here. These make a right triangle, so we can connect them exactly with straight lines. That's gorgeous. All right, find the inverse of the relation. The inverse is when you swap the order pairs. So the first order pair becomes -3, -8. The second order pair, -6, -8. And the third order pair is -6, -3. Graph the inverse. All right, let's switch colors here to graph the inverse. We'll go with orange. So graphing -3, -8, -6, -8, and -6, -3 puts us with this. So describe the graph of the inverse compared to the graph of the original function. Well, notice, kids, that they seem to be kind of a reflection. It looks like you flip it a little, you turn it a little, you translate it a little. Here's the cool thing about inverses. If you were to draw this line right here, and then we can extend it this way as well. Every time you graph an inverse and its original function, it's always going to be reflected over the line y equals x. This is the line y equals x because it goes through the origin, which is the y-intercept, which is 0, and the slope is 1 up 1 over 1. So every single time it is a reflection over the line y equals x. Every single time. All right, so let's take a look at some of the notation and some more definitions. So here is the notation for inverse, f -1 or f to the negative. It's not f to the -1 power, it's just called the f inverse. So if f and f inverse are inverses, then f of a equals b if and only if f inverse of b equals a. So what that's saying is that the domain of f is the range of g and the domain of g is the range of f. The inverse of a function can be found by exchanging domain and range. That's what we just said. Not all functions have an inverse though, and so there's something called the horizontal line test, which you may recognize the words vertical line test to see if something is a function or not, Well, a horizontal line test is to see if something has an inverse. So a function f has an inverse function f negative 1 if and only if each horizontal line intersects the graph of the function in at most one point. So if I have a function here in blue, if I can draw a horizontal line and only cross the function once, then it does have an inverse, and then I can proceed and find it. So here's how we find inverses. So in order to find the inverse of the function, then we're going to graph the function and its inverse. To find the inverse of a function, the first step you're going to do is replace f of x with y. So y equals x minus 3 over 5. So that's step one. Step two is to switch the x and the y. That's because if they're inverses, the domain and range can be swapped. So x equals y minus 3 over 5. Then step three is to solve for y. So if I want to solve for y, I could times both sides by 5. That gives me 5x equals y minus 3. Then I can add 3 to both sides, and that gives me y equals 5x plus 3. The final step is to use function notation for the inverses. So I'm going to say f negative 1 of x is equal to 5x plus 3. So here is my inverse. The steps were 1, change f of x to y. Step 2, swap x and y. Step 3, solve for y. There's your 3 main steps. Now we're going to graph the before and the after to see if, in fact, the functions are reflected over the line y equals x. So let's graph the before. We'll do the before in blue. So we'll do this one in blue. So this is the same as saying 1/5 x minus 3/5. So if I start at negative 3/5, which is an estimate, and then go up 1 over 5, up 1 over 5. I can also go down 1 and left 5, down 1 and left 5. Here is my original function. If I now want to do the inverse function, I can start at 3. 1, 2, 3. And my slope is 5. So 1, 2, 3, 4, 5 over 1. 1, 2, 3, 4, 5 over 1. 1, 2, 3, 4, 5 over 1. And now I can connect these. Again, it's a linear function. And notice that if I were to take and draw the line y equals x, notice that the two lines would land on top of each other. So it definitely is the inverse function, and you can verify that with the picture. Okay, if we look at letter B, we need to find the inverse. So we're going to do y equals 3x squared. That's the first step. Second step is to swap the x's and the y's. So 3y squared. Step three is to solve for y. So I'm going to divide everything by 3. So that gives me x over 3 equals y squared. And then I need to square root. So I'm going to say y equals, and remember when you square root something, it's plus or minus. And square root x over 3. Last thing I need to do is change that y back to an f inverse, plus or minus the square root of x plus 3. There's my inverse. All right, let's go and draw the original. So y equals 3x squared. Well, I can make a table if you don't know how to do it. I do know that the vertex is going to be 0, 0 if I do negative b over 2a. If I just make a table and plug in values, I can do that as well. Negative 2, negative 1, 0, 1, and 2. I can graph it on my calculator and transfer it over. But if I do this on my calculator, or if I do this with a table, I get 3s here and 12s for the 2s. So negative 1, 3, and positive 1, 3. And then negative 2, 12 is a little bit off, and 2, 12 is a little bit off. So I connect my dots. Luckily, I get a U, which is correct because I was graphing a parabola. Then if I switch to my orange, now you may not have any idea how to graph this inverse function down here. You can use your calculator, or you can remember that if I swap the ordered pairs in the graph, then I'll have the graph of the inverse function. So if I start with 0, 0 and I swap it, I stay 0, 0. If I swap negative 1, 3, I get 3, negative 1. If I swap 1, 3, I get 3, 1. And then I can swap the other order pairs as well. And I get something up here and something up here. And then, oh, this is going to be ugly. So I'm going to try to connect my dots. And oh, I sort of did a pretty decent job. So notice that if you were to draw the line y equals x, that it would in fact match up with each other. Okay, so that's how you find an inverse and how you graph the original and the inverse. Now, what if I'm given two equations of functions and asked to see if they are inverses of each other? So two functions, f and g, are inverses of each other if and only if both of their compositions are identity functions. So I need to find f circle g of x, and I need to find g circle f of x. And if they both equal x, then they're inverses of each other. So if I want to determine whether each pair of functions are inverses, justify using algebra, so that means I can't just graph them, then I need to find f of g of x, see what that equals. And I also need to find g of f of x, see what that equals. And if they both equal the letter x, when I'm done, then they're inverses of each other. So f of g of x means to leave the f alone and to replace g of x with the g of x function, which is x plus 7. Then I need to go to the f function and replace the x with x plus 7. So I have x plus 7 minus 7, which equals x. Okay, that's good, halfway there. Now I need to find g of f of x, so leave the g alone, and replace f of x with x minus 7. Then go to the g function and replace x with x minus 7. So x minus 7 plus 7, that equals x. Since both of the compositions equal x, then we can say yes, they are inverses. If one of them equaled x and one of them did not equal x, then they are not inverses. They both have to equal x in order to be considered inverses of each other. All right, let's take a look at two more examples of inverses. Determine whether each pair of functions are inverse functions. Explain your reasoning, obviously, or you justify using algebra. So my functions in part A, f of x equals 3x minus 3, and g of x equals 1/3 x plus 4. So I need to find f of g of x and see if it equals x. So leave the f alone and replace g of x with 1/3 x plus 4. Then go to the f function and replace the x with 1/3 x plus 4. So 3 times 1/3 x plus 4 minus 3. So if we distribute the 3, we get x plus 12 minus 3. That's x plus 9. Well, that does not equal x. So no, they are not inverses. I don't even have to try the other composition because already right away, no, they're not. All right, let's take a look at this last one. F of x equals 2x squared minus 1, and g of x equals the square root of x plus 1 over 2. So let's check f of g of x first. Leave the f alone. Replace g of x with square root x plus 1 over 2. Now go to the f function and replace the x with square root x plus 1 over 2. So 2 times the square root of x plus 1 over 2 squared minus 1. So remember, when you square a square root, those cancel out. So we have 2 times x plus 1 over 2 minus 1. Well, when I multiply 2 and x plus 1 over 2, the 2's cancel, and I have x plus 1 minus 1, which equals x. Ooh, okay, that's good, halfway there. Now I need to find g of f of x. and see if it also equals x. So leave the g alone, replace f of x with 2x squared minus 1. Then go to the g function and replace the x with 2x squared minus 1. So we have the square root of 2x squared minus 1. There's still a plus 1 in the numerator, and there's a 2 on the bottom. So if I simplify the numerator, I get 2x squared over 2. If I cancel the 2's, I get the square root of x squared. And the square root of x squared is x. So since we got them to both equal x, yes, they are inverses. All right, kids, that's the end of this section. If you guys have any questions, please let me know. And as always, keep calm and keep trucking.